More and more each day we encounter machine learning. With so many diverse applications of machine learning, it can be too much to categorize, but I'll highlight a few key areas. Computer vision includes applications like fingerprint detection or facial recognition on your phone, or autonomous vehicles. Natural language processing machine learning includes tasks such as conversations with Siri or Google, spam detection, and auto-suggestions for emails and messages. Customer segmentation includes recommender systems for Netflix or Amazon, as well as market research. Data analysis includes applications like fraud detection in credit card transactions and traffic prediction. These are just a few of the ways we encounter machine learning every day. Machine learning exists at the intersection of mathematics and computer science. Statistics and probability form the mathematical foundations of many of the algorithms we'll learn. AI and computer science pushed the frontiers of what computers could do, which made machine learning possible. There have been many times in the history of AI where great ideas lay in the dust until computing power reached a point that would enable implementation. There are many definitions of machine learning. Here's mine. Machine learning trains computers to accurately recognize patterns in data for data analysis, prediction, or action selection by autonomous agents. The human mind is the best general-purpose pattern recognition machine, but computers can beat humans in narrowly defined tasks given enough training and data. Nothing can be learned without data. The wide availability of data in recent decades has enabled application of machine learning techniques in increasingly diverse fields. Data collection and use is not without controversy. In your projects, you should always make time for ethical considerations. Who owns the data? Who are the subjects of the data? Has the data been anonymized? How will the data be used, and how might it impact the subjects as well as the larger community? Accuracy will be a theme throughout the course as we learn many different metrics and consider the difficult question, what accuracy is good enough for the task at hand? There are many subfields in machine learning. Sometimes we just want to understand the data. Clustering algorithms are often used. Other times we want to learn to predict outcomes on new data. The field of reinforcement learning trains autonomous agents, often with deep learning and huge amounts of data. There's never enough data. An autonomous car ran into this truck because a sideways truck on the road is not something that occurred in the training data. We can divide the field of machine learning into categories. Not every algorithm will fit neatly into our categories, but it's a good framework. What I'm calling active learning involves fields like reinforcement learning. Most of machine learning falls on the left branch here, what I'm calling informative learning, learning about the data. Informative learning has two main branches: supervised learning, where we train data on pairs of XY data points, where X represents a matrix of predictor fields and Y represents a target. For example, learning if a person is a good credit risk, the target, based on their income, age, and other factors. All of those other fields being predictors. Unsupervised learning just looks at fields without designating one as a target. An example might be recommender systems, which cluster customers according to their preferences. Supervised learning is again divided into two main categories: regression, where the target is a real number, like the selling price of a house, and classification, where the target is membership in a set of classes, like a binary classification for a good credit risk versus a not so good credit risk. Do we really need machine learning? To answer that, let's first think about the way we traditionally program computers. We first come up with an algorithm to solve the problem, generally to produce the outputs we want given the inputs. Then the algorithm is coded up in a series of rules. It's very deterministic. Given a set of inputs, you know what the output should be. This works great for applications like payroll, for example. What the program is really doing is taking the steps an accountant would take and automating them. There are many problems that just can't be solved with a bunch of rules. A great example is facial recognition. How would you encode a set of rules to recognize your best friend? We don't even understand how our brains do it, so we certainly can't come up with rules for that. But give a computer an algorithm for learning borders and shapes and photos, and it can learn to recognize faces. Another class of problems that need to be solved by machine learning are problems where the scope is just too large. Machine learning algorithms can learn patterns quickly in data that would take people years to go through. In machine learning, we have dozens of algorithms with dozens of variations each that are good at learning patterns from input data and building a model of the data. Because machine learning grew out of both mathematics and computer science, there's a lot of duplicate terminology. Consider this tiny data table for illustration purposes. Each row represents one person. The row can be called an example, an instance, or an observation. Each column represents an attribute or feature of the person. If we're in supervised learning, we'll select one of these columns as the target and all others will be the predictors. Most of our data will either be quantitative or qualitative. Quantitative or numeric data in this table is the GPA, the hours, and the SAT score. Qualitative data is also called categorical data or factors. Qualitative data encodes class membership. In this case, they're literally classes: junior, sophomore, or freshman. Machine learning presents solutions to society, but also some potential problems. They're potential legal problems. If a company's algorithm does harm, to what extent is the company legally liable? There are ethical considerations. Are the algorithms fair? There have been cases in judicial sentencing applications and resume processing applications where the algorithms learned our human prejudices just from the data. There are security issues, keeping AI safe from adversaries. And there are privacy issues. It varies greatly by country as to what your privacy rights are. We all know that AI has suffered from too much hype over the decades. Gartner outputs hype cycles for various fields. Here's the 2019 hype cycle for AI. Each dot represents a subfield and is color-coded according to when it reaches viability. Notice that autonomous vehicles are orange, indicating 10 years before they're fully functional. The hype of a field rises sharply to a peak, and then disappointment sets in. The plateau at the far right is when the field reaches maturity and reaches its unhyped potential. Notice where machine learning and NLP are on the hype cycle. Machine learning is as much a craft as a science, and like any craft, it takes time to learn. Beyond these few weeks in the class, there are tons of free materials out there. And beyond that, I have some specific suggestions for long-term learning. Number 1, be systematic. Have a plan for learning, a regular schedule, and keep a notebook of your activities and your goals. Find mentors. You may be able to find mentors within your organization, your school, or your place of work, but you can also find mentors online. And always do reproducible research. Take notes as you work. Document, 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 so that you can reproduce your work later when you go back to it. I've outlined a typical workflow for professional machine learning projects. The green boxes are for management. The yellow boxes involve data wrangling, and blue involve the actual machine learning. Project control is top-down in most organizations. The departments and people funding the project call the shots. It's up to the team, however, to provide useful feedback in setting realistic objectives. The first step after establishing project goals is data wrangling. Collecting data, even within a company, can have to go through many steps of approval. Then once the data is collected, it has to be organized, cleaned, and processed in order to be useful for the project. The whole data process can take months. After the data is explored, project accuracy goals can be more realistically set. Notice the actual machine learning in blue is iterative. We train, we test, and repeat, making model improvements at each iteration until an acceptable accuracy goal is reached. Data is often divided into train, validation, and test sets. Once the project has reached acceptable results, final reports are created. All of these steps take place with various teams of experts, machine learning specialists, data engineers, and data scientists, as well as domain knowledge experts. Our typical workflow in class will be much simpler. We're going to first explore our data, then perform machine learning, and then evaluation. Our purpose is to learn many machine learning algorithms, both from a theoretical and applied point of view, so you can develop insights into which algorithms to apply to different problems. But keep in mind that real-world machine learning projects are much more complex than what we're doing in class. In the rest of the video, we'll go through a quick probability review, emphasizing the information that we'll need for the first algorithm we look at, naive Bayes. A random variable can be discrete or continuous. The joint probability is the probability of both x and y occurring. In the diagram, we can see that as the overlapping space between x and y. The conditional probability is a probability that one event occurs given that some other event occurred. If we know that y occurs, what's the probability of x? For example, given a positive disease test y, x would be the probability that you actually have the disease. Conditional probability starts with the joint probability and divides it by the probability of y. Some basic rules of probabilities let us compute unknown probabilities from known probabilities. The product rule lets us compute the joint probability if we know the conditional probability of A given B and the probability of B. The sum rule lets us compute the probability of a variable if we know the joint probability of A over all probabilities of B. The chain rule lets us calculate any number of joint variables using conditional probabilities. Two important values, sometimes called moments, are the mean and the variance. The expectation or mean is the first moment. For example, the expected value of a fair die is 3.5. The variance is the second moment. It's the difference between the variable and its mean squared. If we take the square root of the variance, it's the standard deviation. Next, we look at probability distributions using R because R will give us a nice visualization. It's important to understand our data in terms of these distributions. First, let's look at a Bernoulli distribution. This models a binary outcome in a single trial. Let mu represent the probability of the positive class. Let's say I'm terrible at shooting baskets, and mu is 0.2, the probability that I shoot and actually make the basket. Notice that one of these terms will disappear based on the binary choice of 0 or 1. So the probability that I miss plugging in x equals 0 gives us an 80% chance, and the probability that I make it, where x equals 1, is a 20% chance. The binomial distribution models a binary outcome over a number of trials n. The binomial distribution of x, where I make k baskets in n trials, has this form. And let's say k equals 20 for 100 trials. Will the outcome of the binomial be 0.2? No, it's not, because there are many ways we can get 20 baskets out of 100 trials. 100 choose 20 to be exact. What's the expected mean of our 100 trials? The expected value will be n times mu, which in our case is 100 times 0.2 is 20. Let's derive these values using R. First, we make a vector of possible values for k, the number of baskets made, which can be from 0 to 100. Then we multiply each k by its probability and add them together. E is 20, as we expect. The plot here shows the expected value at the center with variance calculated as n times mu times 1 minus mu, which is 16 in our example. Now suppose that I got really lucky when I shot my first 3 hoops and made all 3. That gives me a mu of 1. It's unlikely I can keep this probability up over the long haul. In fact, small sample sizes serve poorly as prior estimates of probabilities. Instead of a prior mu, we really need a prior distribution over mu. We want this prior distribution to be a conjugate, a family member, of our binomial distribution. The beta distribution is a good choice. The first term with the gammas serves as a normalizing constant to make sure the total probability integrates to 1. Let's look at the beta distribution for example in R. We use the R beta function to create 100 random beta samples with shape parameters 20 and 80. Then we plot this curve as the black line. Now suppose I take 15 more shots and make 5 of them. This will make parameter A 30 and parameter B 85. This updated curve is shown in red. The par nu equal true parameter is used when you want to plot over an existing plot. The beta equation gives us a way to update our model and calculate new probabilities. So far, the distributions we looked at represent binary variables. Next, we look at multinomial variables, variables that can take on more than 2 classes. This formula gives the probability mass function of a multinomial distribution, where k indexes over the number of classes, k, and each of the m sub i's represents the probability of that class. All of the m's will sum to 1. The iris data is an example of a multinomial distribution. There are 3 classes. If we want to put the 150 flowers in the iris data set into 3 boxes or 3 classes, with an even probability of each class, we could use the R multinomial command here. The output gives us 10 vectors left to right because we said n equals 10. Our size is 150 for each column. We get 150 flowers in each column. Values in each row are the number of flowers in that class. The mean values for the 3 rows are 54, 50.1, and 54.9. The Dirichlet distribution is the conjugate prior of the multinomial distribution. The Dirichlet distribution has k parameters, alphas, 1 for each class. So instead of x being 0 or 1, it can take on k values. In this equation, alpha sub 0 is the sum of all alphas. You can think of the Dirichlet distribution as a multinomial factory. Here we ask for 10 distributions with all our alphas equal to 1. The sum of every row, which is a distribution, is 1. The mean of the columns for these 3 examples are 0.2, 0.38, and 0.39. When we ran with 1,000 examples, the means were closer to 0.3 each. All of those previous distributions model qualitative data. What about quantitative data? We can model our quantitative data with a Gaussian distribution, a normal distribution, with this formula here. Its shape is defined by its mean and its variance. The first line in the graph has a mean of 0 and a variance of 1. That's the black line. The blue line has the same mean but a variance of 2, and the orange line has a variance of 0.5. Different means would shift the curves right or left. The variance indicates how sharp or flattened out the curve is. Hopefully, this was a brief review for you of some probability distribution terminology. It's helpful to understand our data in terms of these distributions, and familiarity with these terms will help you read published papers in machine learning conference proceedings.